So let's take a look at how we can use a function definition to help us find limits. So given a function f of x is equal to 2x minus 1 if x is less than 1, and negative x minus 1 for x greater than 1, we're going to go ahead and find a couple of limits here. So first of all, let's go ahead and take a look at the graph of this function. So first of all, we know that the behavior of the function changes when x is equal to 1. So let's go ahead and locate 1 on the x-axis. And here it is marked, and I will go ahead and label it. So for x less than 1, we have a line. Our line is 2x minus 1. So negative 1 is the y-intercept. And it has a slope of 2. So let me put in a few points so that I can draw this line. So, and notice that 1 is not included in that component. So I'm going to make this an open circle there. And I've got a few points. And so there's the behavior of this function for values of x that are less than 1. I'm going to choose a different color, orange. Now, for values of x that are greater than or equal to 1, we have the line negative x minus 1. Negative x minus 1. So I'm going to, there's negative 1. And what I'm going to do is draw in the line and then erase the portion of the line for which x is not less than or equal, or greater than or equal to 1. So let's see here. We've got negative 1 as our y-intercept, and we have a slope of negative 1. So let's draw in a few points on my line so that we can draw in the line. Okay, there we go. Now, remember that this is only valid for values of x greater than or equal to 1. So we're not going to have the line defined here where it crosses the x-axis. We're only going to have the portion of the line to the right of x equals 1 on the x-axis. So there we go. So that's how the graph of our function looks. So let's go ahead and take a look at these limits. So first of all, we have the question of how does my function behave, or the limit as x approaches 1 of f of x. So looking at my graph here, I can see that as x approaches 1 from the left, my function is increasing and headed towards 1. And as x approaches 1 from the right, I can see that the graph is increasing in that direction. But it's not approaching 1, it's approaching negative 2. So there's a couple things we can do here. So we're going to make a note. Let's see, from the graph, the limit as x approaches 1 of f of x from the left, we said was 1. And the limit as x approaches 1 from the right of f of x is equal to negative 2. So if we don't get the same limit from the left as the right, so negative 1 does not equal, so 1 does not equal negative 2, we would say this does not exist. And so we can see that from the graph. Now let's go ahead and use the function definition. Now, since we're using the function definition, and we notice that we're looking at the behavior as x approaches 1, and this function behavior is split at 1. In other words, it has one behavior to the left of 1 and a different function behavior to the right of 1. We need to look at the limit from the left and from the right. It doesn't matter which one we do first, but we need to look at both. So let's do the limit as x approaches 1 from the left. Now from the left, are values smaller than 1. So we'll be looking at 2x minus 1. Now, as x approaches 1 from the left, 2x minus 1 will approach 2 times 1 minus 1, which simplifies to be 2 minus 1 or 1. And then we need to look at the limit from the right as x approaches 1. Okay, and from the right, we're looking at values of x that are bigger than 1. So we're looking at the portion of the function x minus 1, which would be as x approaches 1, negative x minus 1 would approach negative 1 minus 1, or negative 2. So notice we get the same result, which shouldn't be surprising. And so what this tells us is that the limit as x approaches 1 of f of x does not exist. Now, looking at our second limit here, we want to see how the function behaves as x approaches 3. Well, here's 3 on our x-axis. So we're looking at this component or this portion of the graph. And from the graph, it appears that the limit as x approaches 3 from both sides is negative 4. So let's go ahead and use the function definition. This time, we're interested in when x approaches 3. Well, 3 is not less than 1, so we're not using the 2x minus 1 piece of the function. 3 is greater than or equal to 1, so we will be using the negative x minus 1 portion of the function. So we would have the limit as x approaches 3, the part of the function we need is negative x minus 1. And as x approaches 3, negative x minus 1 approaches negative 3 minus 1, which is negative 4. Look at this new function. We've got f of x equals 4 times the absolute value of x minus 3 over x minus 3. And so you might be wondering, well, what about this requires the idea of a definition? But we're going to look at what does the definition of absolute value tell us about the absolute value of x minus 3 here. So recall that the definition of absolute value, so absolute value of x, the absolute value function, gives us the value of x if x is greater than or equal to 0. If x is less than 0, it gives us the opposite of x. So for example, if x is negative 2, then the absolute value returns the opposite of negative 2, which is positive 2. So we're going to use this idea here with the absolute value of x minus 3. So what do we get? So it's going to be 4 times x minus 3 over x minus 3 if x minus 3 is positive, or greater than or equal to 0. And it's going to return to us the opposite. So I'm going to put a negative 1 here of x minus 3 over x minus 3 if our x minus 3 happens to be negative. Okay, well, let's simplify things up a little bit here. If x minus 3 is greater than or equal to 0, we can add 3 to both sides of that inequality, and we get x is greater than or equal to 3, which means for the second part of our function, we'll be looking at x less than 3. Now let's look at how these two pieces of function behave. Notice that when x is greater than or equal to 3, we have an x minus 3 and an x minus 3 in the numerator and denominator as factors, so we can simplify that. So when x is greater than or equal to 3, this function definition simplifies to 4. And when I look at the function definition when x is less than 3, I see something similar occurring. X minus 3 over x minus 3 simplifies to 1. So this portion of the function should simplify to negative 4. So our original function of 4 times the absolute value of x minus 3 divided by x minus 3 can actually be simplified to in a form in piecewise form of 4 when x is greater than or equal to 3 and negative 4 when x is less than 3. So looking at our graph, here is 3 and our function is 4 when x is greater than or equal to 3. So we'll have a point there and our function goes to the right like so. And our function is negative 4 when x is less than 3. So here's 3, here's negative 4. That will be an open circle because this piece of the function of being negative 4 only occurs for values of x less than 3. So now we're ready to find the limits. The limit as x approaches 1 from both sides. So let's find 1. Here's 1 on the x-axis. When x approaches 1 from the graph, we can see that that equals 4. And 1 is, so we ask ourselves, first of all, is 1 greater than or equal to 3? And that's not true. So we're not using the first portion of the function. Then we ask ourselves, is 1 less than 3? Yes, that's true. That means that f of 1 is equal to negative 4. Limit is what happens when x approaches 3. So we have 3 already identified, and we can see that our limit from the left, as x gets closer and closer to 3 from the left, our limit is negative 4. And as x approaches 3 from the right, our limit is positive 4. And we can also see that based on our function definition. Let's go ahead and look at that. The limit as x approaches 3 from the left. So values that are smaller than 3. X less than 3 means values that are smaller than 3. So this limit would be negative 4. And then if we check it from the right, the limit as x approaches 3 from the right of f of x. Well, if x is approaching 3 from the right, those are numbers that are bigger than 3. So we'll be using the first part of this function, and that would equal 4. Note that -4 does not equal 4. So we can comfortably say that the limit as x approaches 3 of f of x does not exist. I hope this helps.